the principle of virtual work for a rigid body. So that means that the body is rigid and it doesn't deform, or the rigid body is statically determinate in that it won't deform under the virtual forces. So we had an example last time. Pretend that rubber is a beam, and pretend that rubber is a beam. So if I apply an imaginary force, or if I apply a virtual force to it, then the sum of all the external virtual work must be equal to 0. So that's effectively saying you're not making up energy, but we can make up a displacement or we can make up a force. So there are two principles to apply. Let's have a look at the first one. If a rigid body is in equilibrium under the action of concurrent forces, which you would have in a statically determinate structure, then the virtual work done by the forces during any compatible virtual displacement is equal to 0. And the second one is, if a rigid body is in equilibrium under the action of concurrent virtual forces, then the virtual work done by the forces during any real displacement is equal to 0. So let's have a look at the application of that of those statements to a beam. So for argument's sake, and remember, we're thinking about work done. So that means that if the virtual forces act in an opposite direction to the displacements, you get a negative value, and if they act in the same direction, you get a positive value. So that's effectively saying if I walk in that direction, I'm doing work. If I walk in that direction, I'm also doing work. And the two values of work are the same. It's not like I'm doing negative work moving in that direction as opposed to that direction. So let's have a look at a simply supported beam. So we'll draw a beam there. And this time, let's assume that I've got a force acting on the beam. So that end is pin and that end is roller. And I'll invent a coordinate system as we go along. And just to make my life easier, when I break up that force acting at 45 degrees, let's just assume it's going to be 1 and 1. So that end is already on the roller, and that ends on the pin. So we've got a horizontal force A, and we've got a vertical force RA. And on the other side, I've got a vertical force RB. So we don't actually need to use the principle of virtual work to work out the horizontal forces, because we should be able to say that the horizontal force HA must be in equilibrium with this horizontal force. HA therefore acts from the left to right direction to be in equilibrium with that force, and the value of HA must be equal to 1 kilonewton. But because we're going to be applying this theorem of virtual work to more complicated examples, let's just satisfy ourselves that the principle of virtual work is okay for this problem. So effectively, I'm going to say, let's move the whole body across by a distance delta. So we've got our rigid body, so it's a rigid body translation, not transformation. So I'm moving my rigid body across. The amount by which I'm moving my rigid body across is I'll call that delta. And I'll just stick a bar on to let you know that's a virtual force. So, sorry, a virtual displacement. Now, this value, delta, you could say, what is it? It's a very, very small value. So this value, delta, is very, 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 very small. Okay? So it's a really, really small, it's like a micron. All right? It's less than a micron. but so I've obviously shown it on an exaggerated scale, but it's really, really, really small. So now up here we've got RA, and down here we've got RB, and we've sort of broken the pin because you've got this HA, and let's apply the principle of and we've also got this HA. So let's apply the principle of virtual work for a rigid body or a rigid body in equilibrium under the action of concurrent forces. So we've applied a rigid body displacement of delta, or a virtual displacement of delta. So let's apply the principle of virtual work, and let's say how much work each of the forces has done. So the sum of all the work done must be equal to 0. So HA has done some work, and HA has also moved this distance, this very small distance, delta bar. So the work done by HA is HA times delta bar. And onto that I add on how much work my 1 kilonewton has done. So when I say my 1 kilonewton, I'm obviously talking about that 1 kilonewton. Now note that my 1 kilonewton is acting in an opposite direction to the direction of the virtual displacement. So it's also done times delta bar, but because it's acting in the opposite direction, I'm just going to stick a negative sign in front. So that then means HA times delta bar is going to be equal to 1 kilonewton times delta bar, and that means that HA is going to be equal to 1 kilonewton. So this theorem of the theorem of virtual work for a rigid body seems to work, in that you apply a virtual displacement, which can be anything, work out the work done as a result of doing that virtual displacement, and by some sort of principle of work, that the total work done must be equal to 0, you're able to work out some forces. So sometimes, just for convenience, instead of putting 1 delta bar and then having to cross out the delta bars, sometimes if you just want to jump a step, you could just not call it delta bar, but you could just call it 1, because we know that it's all going to cancel out in the end, and then the delta bars disappear on that side, the delta bar disappears on that side, and you immediately get HA is equal to 1 kilonewton. So if you get stuck, just write the delta bars. If you're satisfied that the delta bars are going to cancel each other out in the equations, just pretend it's 1, and then you don't need to worry. Then you directly say HA plus negative 1 kilonewton is equal to 0. HA is equal to 1 kilonewton. So sometimes if we jump a step, don't worry too much. So now let's have a look at another example. So you'll probably see where this is leading to. So in this example, this time I want to solve the reaction there, and I want to solve the reaction there. So looking at the beam, of course the vertical reaction on both sides is going to be equal to 1. But let's just see if the theorem of virtual work can take care of that for you. So our unknown is RB, so we don't know what RB is. So, because we don't know what RB is, let's stick a rigid body translation on the system, and let's rigidly move RB up. So that's the virtual work that we have done. Okay. So I've got my 1 bar there as 1 micron or 1 imaginary unit by which I've displaced my structure. And remember that my structure is a rigid body in equilibrium under the action of concurrent forces. So I've rigidly moved my structure up by 1, and all this of course is imaginary or virtual. So now if I've moved the end of it up by 1 bar, just by similar triangles, this bit here under that load has moved up by 1 bar over 3. And this bit up here has moved up by 2 bar over 3. Okay? So it's just all based on geometry. So let's apply our theorem of virtual work. Let's apply our theorem of the principle of virtual work, which means that the theorem of the principle of virtual work is that no work is done. So in this case here, my force is acting downwards, yet my displacement is upwards. So I'm going to stick a negative sign on whatever I'm going to multiply the two against. So it's going to be minus 1 kilonewton multiplied by 1 bar over 3. Because my force is working in an opposite direction to the virtual displacement. Okay? So let's add that on to the work done by this force there, and the work done by this force there is 1 times 2 bar over 3, because that displacement is 2/3 of 1 bar. And again, I'm sticking on a negative sign because the force acts downwards and my virtual displacement is acting upwards. And now let's finally deal with the RB. So the RB does work in the direction of the virtual displacement. So because the two are working in the same direction, it's going to be positive. So it's RB times 1 bar. So as I said, you can forget about all the 1 bar nonsense. Just call it 1 and those problems disappear. But if you want to see it, you can put the 1 bar in, or you can substitute delta bar for 1 bar if you really want to see this virtual displacement. So we add all these up, sum them to 0. We get the 1 bars cancel each other out, or the bars cancel each other out. So we get minus 1 over 3 minus 2 over 3 is equal to minus negative RB, and we get RB is equal to 1. Okay, so we can see that this theorem does work, and we can probably extend the theorem further to say from 2-point loads you could try it for a UDL, for example, and it will still work. And if you want a confirmation that you have indeed correctly calculated what RB is, then look up here, and that's when I do moments about A. So moment, so this is the way the Eng course would have taught it, moment about A. So you take moments about A, 1 times that distance plus 1 times that distance is equal to RB times the whole distance L, and out pops RB equals 1. So we've confirmed, I believe, that this principle of virtual work does indeed make sense, and it does indeed work. Okay, so that's the theorem of virtual work. Apply a virtual force or a virtual displacement, and then we can work out our reactions for statically determinate structures or rigid bodies in equilibrium under the action of concurrent forces, which is what a statically determinate structure is. So, having